think on our L to J a few times, the minor arcs and the symbol for arc, some of those things came up, so finally we're to the lesson that deals with those. On a circle, you can have different kinds of angles, and that's what we're going to be looking at tomorrow quite a bit. But today we do have what's called a central angle. Central angle is an angle whose vertex is the center of the circle. Can you understand why they would name it central angle? Where else did we have central angles so far in our class? What'd you say? Regular polygons? The center point on regular polygons, we had central angles that were drawn there. We did 360 divided by the number of sides there were. Well, to find the measure of a central angle in a circle, we don't have sides to go with. But it is at the center of the circle also. Another term today is an arc. An arc is just an unbroken part of a circle. So if the circle is the continuous curve, an arc would be part of that curve. Maybe a fourth of it, maybe half of it, maybe 3/4 of it. But just part of that curve is referred to as an arc. Has 2 points, we'll name it by its 2 points, which are going to be its endpoints, and then all the points on the circle between them. So that's what an arc is, part of a circle. So here are the 3 different categories of arcs, and you have something in your notes that has part of this on it. A minor arc. Minor refers to things that are smaller or maybe less significant. The minor arc is an arc whose points are on or in the interior of a central angle. So you can see the picture of the central angle, the angle that's at the center of the circle. There technically are 2 arcs that we could talk about on this picture. If we want to talk about the small arc, we use this type of notation. Measure of arc AC. When there's 2 letters, the ends of the arc are the ends of the shorter arc. So the minor arc is the red one from A to C. We measure arcs in degrees. We will also find how long they are. But there is a difference between the length of an arc and the measure of an arc. It might seem like in your head that they're the same thing, but no, they're used differently. So when we refer to the measure of the arc, it's how many degrees the arc is. And it's always related to the central angle. In this case, for a minor arc, it's the very same as the central angle. Central angle is x degrees, the minor arc is also x degrees. So that would be maybe an 80-degree central angle. So that's an 80-degree arc. A major arc is bigger. So notice its name is longer. That's because you go the long way around on the circle. So A and C are both the endpoints, but looking at the arc, you have to pass through point D. So ADC highlighted in red, that would be the big arc, the major arc. A major arc is going to go more than half of a circle. I don't really like the way that that's described. It says it's the points on the exterior of the central angle, so it's like on the back side of the central angle. You might write down in your notes to add to that a major arc is arc that is more than 1/2 a circle. So you go the long way around instead of the short way. So if you're going more than half a circle, what kind of degrees will major arcs be? Over 180, correct. They will be more than 180 degrees. So we can find them by subtracting. So here's what their explanation is. I'll stick with this 80 degree. If this is an 80-degree central angle, the major arc would be 360 for all the arcs around a circle. 360 minus 80 degrees. 360 minus 80 is 280. So this red arc is a 280-degree arc. So they're getting it by taking 360 minus that central angle. If we know how big the arcs are that go together, we can add, depending upon what information we have. But in this case, based upon the information, you had to subtract. So if this is a 60-degree central angle, the major arc would be 360 minus 60, 300 degrees. So keep in mind the 360 because of the total degrees of an arc or of the central angle. And the last term you're probably very familiar with, semicircle. We were doing hemispheres in the last chapter. Same idea, but your flat circle. Semicircle is going to be exactly half of a circle. So the degree measure will always be 180 degrees. We do have to use 3 letters to name a semicircle because if I would just say arc EG, the top arc and the bottom arc would both be arc EG. Yes, they're the same degrees, but they are different parts of the circle. So if you want to clarify which part of the circle you're talking about, you have to include a third point. So the top part would be arc EFG. The bottom one, I'm going to have to add another point on there. We'll get an H. The bottom arc is arc EHG. Same measures, but different halves of the circle. All right, so if you want to name a minor arc, a small arc, how many letters in the name? 2. Just the endpoints. If you have 3, that means the arc is how many degrees? Could it be 180? Yeah, it could be. Or it would be more than 180, going the long way around. So that symbol up on top, it's not straight across. It does have a curve to it. So that is an arc symbol that is up on the top of those. Any clarifying things on there? We just reviewed that. Okay, it says practice naming arcs and locating, or naming and locating arcs. So let me go back one and make a picture on the board for you. And have you name some arcs. Why don't you grab a marker board so I can check that you're using the right notation. Make a big circle. I'm going to clarify that goes straight across. Probably enough. I would like you to name 3 minor arcs for me. 3 minor arcs. Now, if you put the M in front of it, you're talking about what's the measure of it. So really, if you're just naming them, you don't want the M. All right, let's see if we can name some of these. See if you got all of them. Just give me one of your minor arcs. Arc AC. AC goes through point B, so do I have to include point B when I name it? No, because that's not a major arc. So arc AB, or AC was one. Give me another one, Zach.
CE.
Arc CE. Okay, another one, Paige. FE. Another one. AB. How many could there be? 1, 2, 3, 4. 5 little ones. 6, 7, 8, maybe 9. I can come up with like 9. It's every separate arc, AB, BC, CE, EF, FA. Then I could go arc AC, arc BE, arc FC is less than half a circle. I think even arc FB is less than half a circle. I'm imagining where a diameter would come to. there are quite a few minor ones. Okay, name some major arcs. See if you can get at least 3 major arcs. Letters to make it go the long way. Let me see what your names on your major arcs look like. Getting the curved symbol on top. Okay, so let's see. Did you have D in the name of your major arc? You should not have D, because D is not a point on the circle. So if you have D anywhere, that one's wrong. So a major arc could be what? Shaylee, what did you have?
B-A-E.
B-A-E. Start at B, go the long way, E and then A. Yes, that's quite a bit of the circle. Megan, what did you have?
A-C-E.
A-C-E. A, then C, then E. Oops, that's not more than half a circle. She named a semicircle. Alright. Because A and E are the ends of a diameter, so that would be exactly half a circle. Gotta give them more than that. Okay, Sam?
ACF.
ACF. Yes. ACF, not E. Okay, another one, Riley.
A-B-F.
ABF, yes, and that would actually be the same as ACF, but she did use different points. Yes, Abby? CFB, you said? C, go to F, and then continue to B. That's more than half the circle. Give me another one, Paige. Never mind? Okay. All right, Judy? F, A, and then E, yes. Any others? Keenan?
EFB.
E, F, B, yes. C, F, B, did we do that one? Okay. Would be F, C, and that's the same arc, just from the other side. C, A, E, C, then A, then E, correct? So there's probably some we didn't name. Got the idea of major arcs? Okay, now Megan gave us one semicircle, but there should be 2 semicircles. What's a name for the other semicircle? Arc AFE, correct? And for the ACE, you could also name that ABE, or start with E instead of A. Go backwards, basically. Okay, so we've got all 3 categories. Right. Adjacent arcs. Adjacent arcs, it says, are arcs of the same circle. So they have to be in the same circle, and they intersect at exactly one point. In other words, they'll be hooked together at the end. So in this picture, we've got arc RS and arc ST. Those are adjacent arcs. So on the picture that's on the board, give me 2 adjacent arcs. What are 2 adjacent arcs? Arcs that share an endpoint. Arc AB and arc BC, yes. Another adjacent arcs? Okay. What did you say the first one was? Okay, arc FE and arc EC. Yes, they're connected at F, or at E, I mean. Did I say it wrong? Or did she do? I don't think so. And then one more example, Derek.
FB, arc FEM, arc EC. I could just do that one.
Another one, how about arc FC and arc CA or CB? Okay, so adjacent arcs have to be connected together, okay, at the same endpoint. Why we use adjacent arcs is the arc addition postulate. We had, if you remember way back, we had segment addition postulate. We also had an angle addition postulate that just told us when we could add them together. This talks about adding arc measures together. It says the measure of an arc formed by two adjacent arcs is the sum of the measures of the two arcs. So if you want to get the measure of arc AC in that picture, you can add the measure of arc AB and the measure of arc BC together. You probably would have done that naturally. Let's put some numbers on our picture here on the board. I think this looks like 40-degree angle. This looks like about an 82-degree angle. This one, let's go with this as 130. Okay, I would like you now, I've got a list of arcs and things on the board. I want you to find the measure of each of those arcs that are up here. What's the measure of every arc that we listed on the board? What's the measure of arc AC? The measure of arc AC. There are a few that you'll have to finish calculating. I've given you the central angles, but we had some notes that told us how the central angle relates to the arc measure. There was a diameter in there. I made AE into a diameter. That should help you get some measures figured out. Those major arcs are going to have degree measures that are more than 180 degrees. You could find them by subtracting from 360. You could probably use this arc addition postulate to figure them out also. So you can add arcs together. no way I can check all these just by holding up your board, so keep those on there, we'll run through 'em. Anyone else need better markers? Sure. Good right now? I don't know all the answers off the top of my head, so. I'm checking here. All right, let's start through some of the answers. Okay, AC, I guess this central angle means this arc is 40 degrees. The central angle of 82 means this arc is 82 degrees. And the 130 means arc AF is 130. Okay, so how did you, before I go further, how did you get arc FE? Okay. Okay, the 180 would be related to the diameter that I drew. These are a linear pair, 50, 50. And same over here, that has to add up to 180 total, so let's see, what did I need? 58? Just to have all those numbers. Okay, so arc AC from A all the way to C would be 40 plus 82. It should have been 122. Arc CE, we just got by subtracting from 180, so 58. FE, we got as 50. And then AB was just 40 degrees. Okay, arc BAE, from B to A and keep going to E. So you could add 40, 130, and 50. Or maybe you even thought just 40 plus 180. Anyone do subtracting? I think under that situation I would add also. So what do we get, 220? A CF, that's gonna be 180 plus 50 more, 230. CFB, CFB. I think I'm going to subtract on this one because it's everything except the 82 degree angle or arc. So what's 360 minus 82? 278 for CFB. And then FAE, FAE, that's everything except the 50 degree arc. So 360 minus 50 is the way I'm going to do that one, 310. Arc ACE should be 180 degrees, and AFE should also be 180. You can check that by adding together those. Give me a thumbs up or down. How did you do on that? All right, looks like you're comfortable with that. So we just did our example, I'm gonna skip the one that's on here. And the ones that are on here, we did quite a few. Okay, the next definition, way at the bottom of that page, is congruent arcs. Yesterday we had congruent circles, I've got congruent arcs. Now, take a look at this definition. Within a circle or congruent circles, congruent arcs are two arcs that have the same measure. Now, don't just read the part that says congruent arcs are arcs with the same measure. That's not enough. Because a 90-degree arc in a little circle is a different arc than in a bigger circle. If I would draw a small circle, big circle, make an easy 90-degree arc. If I would put this arc on the small circle, that 90-degree arc, on tracing paper, pick it up and bring it down here, would it match up exactly with this one? No, it'd be in a lot closer, wouldn't it? So it's not just that they have the same degree measure, but they have to be from the same circle or from circles that are the same size in order to get the arcs to match up. So that's why the beginning part, within a circle or congruent circles. So you can word that a little bit differently if it helps. Congruent circles are arcs in the same circle or in congruent circles that have the same degree measure. So we can use the congruent symbol. We're saying arc ST is congruent to arc UV. How do I know they're congruent in this picture? They have the same central angles. So this arc would be X degrees. This arc would be X degrees. They're in the same circle and they have the same degree measure, so that fits the definition. The different size circles cause a problem if you're searching for congruent arcs. If you turn the page, you'll find this. It's kind of a sequence of 3 ideas that go together. Do I need to go back to that last screen? Okay, Theorem 1122, Part 1, Part 2, Part 3. All of these theorems have to be in either the same circle, or if you have 2 circles to do this theorem, they have to be the same size. Okay, otherwise, these theorems really do not work. I think I'll wait for you to write things down so that then you can think about what the theorem's saying. So I'm going to pause a little bit while you're drawing. You might pay attention to what's in red was the hypothesis for this one. The blue's the conclusion. They really shouldn't have drawn that in the beginning part. This one, the blue is the hypothesis. The green's the conclusion. And on this one, the green's the hypothesis. The red's the conclusion. So if you'll just draw the correct hypothesis part, it might help you know which theorem is which. I should have changed that before I had that in here. Make a note to myself. Kind of hard to get rid of parts of that diagram. So that's probably why they color-coded it. So pretty much they've got the same picture every time, but different things highlighted. Okay, the first part says if you have congruent central angles, they will have congruent chords. What was a chord from yesterday? Okay, a segment whose endpoints are on the circle. Okay. So you see in that first picture, we do have chord DE and CV. So this first one is saying that if you have the central angles congruent in this circle, then the chord DE is always gonna be the same length as chord CB. These are kind of nice ones that we can think through proofs on easily. What would be a proof to prove that the blue ones are congruent? Well, you've got those angles given congruent. AE is a radius of the circle. AD is a radius of the circle. AC is a radius of the circle. AB is a radius of the circle. Does the radius in one circle change? No. So by definition of a radius, all of these are the same length. In terms of triangles, can you see side, angle, side, congruence? So your two triangles would be congruent by side, angle, side, and then the segment DE and the segment CB would match up by CP, CTC. Remember back when we used that? So if you have central angles that are congruent, then the chords will be congruent. Okay, the second part says if you start with congruent chords. So if you have these two chords congruent to start with, then the arcs, the curve, arc DE will be congruent to arc CB. How can we come up with that? Again, the triangles, our radius the same length. The triangles congruent by side, side, side. That was a weird noise. And then central angles by CP, CTC. Your definition tells you that the angle and the arc have the same measure. So we could get there through that thought process. And on the last one, if we start with the arcs being congruent, then the central angles will be congruent. And that really just goes back to the definition that we did a while ago. The arc and the central angle have the same degree measure. So if those arcs are the same, the central angles will be the same. We're going to go through a few examples, and one thing I want you to tell me is which part of this theorem is it? Is it part 1, part 2, or part 3? So you might underline what the hypothesis is. Like this first one, the hypothesis is congruent central angles. On the second one, the hypothesis is congruent chords. On the third one, the hypothesis is congruent arcs. We'll see which part we're using. Anyone still need the screen? Okay. All right, here's an example. I want you to find the length of, or the measure, so the degrees of arc WS. So how many degrees is arc WS? What part of the theorem would you use? Does 2 start with 2 congruent chords? Okay, so that's the part you're using. So you're using part 2, read through that. If you have congruent chords, then congruent arcs. So the arcs that are related to those chords are congruent. We would have more to do it for, yeah. You might have to come up with the, and perhaps you'd have to use the first thing to come up with the chords. All right, got it solved? And you answered the question, you just didn't tell me what N is. So WS should have been 88. It's degrees because we're finding the measure of the arc. Any problem solving that one? Okay, how about this one? Let's think through and see what part of that theorem we're using. We have circle C congruent to circle J, so those two circles are congruent, same size. And it gives us central angle GCD in that triangle, and that circle is congruent to the central angle NJM in the other circle. So look through the theorem. Which part is this? Part A, part 1, 2, or 3? Anna, which one? Number 2, we have congruent chords. Not to start with, we don't. Number 3, we have congruent arcs to start with. No, try again. Isn't it number 1? What's the hypothesis for the first part?
Oh, yeah.
Congruent central angles. So it's the angles that they gave us congruent. So this is part 1 from the theorem. So read what it says. If there are congruent central angles, then the chords are congruent. The chords, so segment DG and segment NM, those chords will be congruent. Notice the pointing to that, they don't have a degree, so you know it's not the arc. If it was the arc, it would have a degree symbol on it. So the theorem says if those central angles are congruent, those chords are congruent. So make DG the same length as NM. B, 62, 16, I don't know where I heard a 62. T was 3, so 16. Okay. This must be the last probably example of that theorem. So let's see what theorem part we're using here. It says ray PT bisects angle RPS. What does that mean? Bisect an angle. Divides it into 2. Exactly the same. So what things would be congruent? Okay, not based upon this. If I use this and the definition of an angle bisector, what could I support? He said 2 angles are the same. So what angles are the same? RPT and SPT. Those look like the central angles. So what part of the theorem starts with central angles congruent? Part 1. Right? Okay, part 1. So if those central angles are congruent, then read what it says. I think it says the chords are congruent, isn't it? So make the chords congruent. That's been pretty well solved. Giving you all the thoughts along the way. X was 2. So you get RT to be 12. Thumbs up or down? All right. Well, it looks like I do have one more here. Which part does this use? 2, is that the one that starts with congruent chords? Okay, and it says if there's congruent chords, then the arcs are congruent. So I'm just gonna click through this one. Okay, so you set those two equal to each other and solve. Substitute back in 25 times 4, so 100 was our answer there. All right, so that theorem has multiple parts to it. These are the last two theorems. It says in a circle, if a radius, or it might be a diameter, and sometimes they don't even draw the whole radius. But if it goes to the center of the circle, it would be part of a radius or diameter, so it fits this theorem. In a circle, if a radius is perpendicular to a chord, then it bisects the chord and its arc. If we've got a radius perpendicular to a chord, it's going to bisect the chord. It's going to cut that in half, and it's cutting the arc, EF, in half also. Bisects the chord and the arc. The bottom one sounds like the converse. In a circle, if you have a perpendicular bisector of a chord, that will always be a radius or diameter of the circle. We're going to use this to do a construction, and probably tomorrow we'll do the constructions. To find the center of a circle, what we can do is construct the perpendicular bisector of chords. And we can locate the center of the circle if we don't know where it is. So that one's going to be used more in that way. The top one, I need to show you an example problem so that you get one of the thoughts that if you don't think about it, you might get stuck on a problem on homework. On this bottom one, I wish they didn't have that center of the circle. But if there's a perpendicular bisector of a chord, that thing goes through the center of the circle. So that would be a diameter or a radius. Okay, got that? Case of diameter. All right, an example problem, write this one down. You got room on the bottom of that paper or the back of it. There's something you have to do to this picture. I hope your textbook doesn't have it drawn in, but chances are in half of them it probably is. They have a lot of writing in the book. We're supposed to find the length of NP. Now, if you think about the theorem that we just went over, notice we have a radius, and it is marked perpendicular to the chord. Okay, so what's that theorem say? If you have a radius perpendicular to a chord, then it bisects the chord and the arc. The arc is not going to be important in this problem, but it bisects that chord. Now the 8 and the 9, 8 is from R to this intersection, and 9 is from the intersection to the M. So that length is not 8 or 9. Okay, so here's what you need to do to be able to work the problem. Draw a radius in to complete a right triangle. Draw a radius in to complete a right triangle. You see where that could go, two different places? You could either draw Rn or Rp. And that's going to form a right triangle. You know this length is 8. We don't know NS, but we do know Rn. Rn's a radius of the circle. Rm is a radius of the circle also. How long is Rm? 17. 8 and 9 added together. So using that, you can bring the number 17 for that hypotenuse. Now if you just do Pythagorean theorem, we can figure out the answer to the problem. But a key, drawing in that radius to make a right triangle. So Pythagorean theorem, I'll put an X here. X squared plus 8 squared equals 17 squared. Is that a triple? 8 something 17? 15? If that ends up being 15, so then what's the length of NP? Because we just found half of it,
30.
so double it. We get 30. Watch for that one as you work through some. You feeling like it must be getting close to the bell? Looking to see, there was a second example of that one. And I guess that was about it. All right, page 760 is where we're at. And this is an e-backpack, but just to verify, page 760, 1 through 18, 25 to 28, 30 to 35, 37, 39, 48, 50, 60, 71. Some of those are simply like we did at the beginning, name and a major arc, name a minor arc, find the degrees. Probably kind of a quick assignment. Don't forget to work on your cumulative test a bit more.